Okay, let's dive into the basics of how GPU and TPU work. Think of a GPU as a super efficient engine built for handling many tasks simultaneously, like rendering complex graphics in games or editing videos. They are designed to do the same thing over and over again with lots of data at once. A TPU, on the other hand, is specifically engineered for the demands of machine learning, particularly training big neural networks. It's built around a core operation called matrix multiplication, the heart of many deep learning algorithms. Basically, TPU are great for general-purpose parallel processing, while TPU are specialists in AI. Okay, let's talk about the differences between these processors. Your standard CPU is like a really skilled generalist. It can handle almost anything you throw at it. It has just a few powerful cores and is built for running your operating system and everyday apps. Next up, we have the GPU, which was originally designed for graphics processing but has become incredibly versatile. It's got hundreds or even thousands of smaller cores, all working together to do massive amounts of calculations very quickly. Finally, there's the TPU, specifically designed by Google for accelerating machine learning tasks. Think of it as a super specialized tool that's exceptionally good at handling those complex tensor operations that are at the heart of deep learning. Okay, let's talk about how we get these accelerators like GPU and TPU so fast. The key idea is something called parallel computing. Basically, instead of a computer doing things one step at a time like your regular CPU, it can split up a big problem into many smaller pieces that can be solved all at the same time. Imagine an assembly line where different workers are tackling different parts of a product simultaneously. Data parallelism is especially important for these accelerators. It's about applying the same operation to lots and lots of data in parallel, which makes them incredibly efficient for tasks like image processing or machine learning. Okay, let's talk about how GPU and TPU get so fast. The key is parallel processing. We have two main models here, SIMD and MIMD. SIMD is like having a single worker on a production line who does the exact same thing to every item passing by. Think adding numbers in an array. It's really efficient for doing repetitive tasks on lots of data. On the other hand, MIMD is more like having a whole team, each working on a different part of the problem at the same time. GPU and TPU are masters of MIMD because they have tons of cores that can tackle completely independent calculations all at once. Okay, let's talk about how GPU manage their memory. Think of it like a tiered system, from super-fast registers directly in the processor's core to the much larger global memory where everything ultimately lives. The key is that data moves between these levels, and we want to make sure it moves as little as possible. So, we're looking at how to organize our data so it's close to where the processing happens, minimizing those trips back and forth to slower memory locations. By arranging things in a way that allows us to access them sequentially like a line of soldiers and using data structures that are friendly to caching, we can really speed things up. Alright, let's dive into how TPU are a powerhouse when it comes to matrix multiplications. Unlike your standard CPU, which tackles these calculations one step at a time, TPU use something called systolic arrays, really efficient parallel pathways. It's like an assembly line for numbers. These arrays eliminate a lot of wasted work and speed up memory access, making them incredibly fast. And it's not just about the hardware. Things like optimizing the way data is arranged, combining operations into one step, and processing larger chunks of data all play a big role in getting the most out of your TPU. Okay, let's talk about how to really make your GPU shine when it comes to processing large amounts of data at once. The core idea behind optimizing for batching is that instead of running through each individual piece of information one by one, which can be slow, we group them together into a batch. This means the GPU does all its calculations on a collection of items simultaneously, significantly reducing the time it takes to process everything. Finding the right batch size is important. Too small and you spend a lot of time just moving data around, and too big, and you might run out of memory. There are techniques like dynamic batching where the size changes depending on your data, padding to make batches equal in length, and even prefetching, which moves the next batch of data into memory as we're working on the current one. Okay, let's talk about a really effective way to boost GPU performance, kernel fusion. Think of it like combining multiple small tasks into one big, efficient job. When you launch several tiny kernels individual sets of instructions, the GPU has to spend time setting up and switching between them. Kernel fusion eliminates this overhead by treating those smaller kernels as a single, larger operation. This means less wasted effort on launching and managing each kernel individually, which translates directly into faster execution times, better memory usage, and ultimately higher throughput. Okay, let's talk about memory coalescing in Qt. It's huge deal for getting the most out of your GPU. Basically, when threads are accessing data together in memory, it's like they're working as a team. The GPU can fetch that data much more efficiently if all the threads in their warp group of 8 threads are looking at nearby locations in memory at the same time. This is called coalescing. If threads aren't doing this, the GPU has to make lots of small trips to grab the data, which dramatically slows things down. There are a few ways you can encourage coalescing. First, use stride 0-axis, meaning threads in the same warp look at consecutive memory locations. Second, make sure your arrays are laid out correctly, usually in row major order. And finally, sometimes loop transformations can help. Think of it like this: if all your team members work together efficiently and grab the supplies needed for a project, you'll get to the finish line much faster than if everyone grabs their own little piece at random. Let's dive into how NVIDIA GPU really speed up deep learning with tensor cores. These are specialized hardware blocks designed specifically to handle the massive matrix calculations that underpin most neural networks. They work by performing these operations in low precision formats like F16 or BF16, which significantly reduces memory usage and power consumption compared to traditional calculations. Think of them as super efficient calculators for your models. To get the most out of tensor cores, it's helpful to experiment with different data types and make sure that the layers in your model are positioned to take advantage of this acceleration. Okay, let's talk about quantization. Think of it as squeezing data to make things run faster. We're talking about reducing the precision, basically shrinking the numbers used in our neural networks. There are a few ways to do this. First, you can apply asterisk after asterisk training your model. That's called post-training quantization and is pretty straightforward. Then there's quantization-aware training, which involves retraining with quantization in mind for potentially better accuracy. Finally, dynamic quantization adjusts the precision on the fly based on the data itself. We often use levels like int8 or F16. It's all about finding a balance between speed and maintaining good results. Okay, let's talk about mixed precision training. Basically, it's a clever way to speed up deep learning models by using slightly less precise numbers, specifically 16-bit floating point instead of the full 32-bit versions. It doesn't mean we're sacrificing accuracy. In fact, modern hardware and techniques like automatic scaling help ensure that the results remain very close to what you'd get with full precision. It's a really effective way to make your training runs faster and use less memory. Okay, let's talk about shrinking the size of our models. A huge challenge when working with really big AI models is memory. They can take up a lot of space. So how do we tackle this? Well, there are several clever techniques. First off, quantization is a super popular one. It's like reducing the precision of the numbers used to represent our models' weights and activations. Instead of using 32-bit floating point numbers, which take up a lot of space, we can use 8-bit integers. That's a massive reduction. Next, pruning is where we identify connections in the network that aren't really contributing much to performance and just remove them. It's like trimming the fat. Then there's knowledge distillation, which involves training a smaller, faster model to imitate the behavior of a larger, more complex one. Finally, you can even split up your model across multiple GPU or CPU if that helps. It's all about making the most of what's available. Okay, let's talk about 2 key ways we can boost performance on GPU and TPU. First up is layer fusion. Basically, we're combining multiple consecutive layers into a single new layer. This minimizes the number of times the GPU has to launch kernels, which significantly cuts down on startup time and helps keep data closer together in its memory cache. It's like streamlining a process. Then there's operation reordering. This involves rearranging how we perform operations within a layer. We can change how tensors are arranged in memory or even tweak the order of loops to better utilize the GPU internal architecture and reduce those costly data transfers, which is where much of the performance bottleneck often lies. Okay, let's talk about a really important part of getting the most out of GPU and TPU, minimizing the data transfer between your CPU and those powerful accelerators. Think of it like this: the CPU is good at general tasks, but the GPU/TPU are specialists. However, if you're constantly shipping huge chunks of data back and forth, it becomes a bottleneck. There are several ways to tackle this. First, try to reduce the size of your data itself. Compression can be really effective here. Second, use asynchronous transfer so that the CPU doesn't have to wait for the GPU to finish before moving on. Then, consider dividing your large data sets into smaller chunks and transferring them in batches. Finally, make sure your code is organized to access memory in a contiguous way. This is called memory coalescing, and it can dramatically boost bandwidth. Okay, let's talk about getting the most out of GPU and TPU, specifically how we handle tasks to really boost performance. The key here is moving beyond doing everything in a straight line. We're diving into asynchronous execution and stream management. Think of it like this: instead of waiting for one step to finish before starting the next, we can issue multiple instructions at once. The hardware then takes care of coordinating them. It's like a super efficient sorting facility. And alongside that is stream management. Data moves through these continuous pipelines, minimizing delays and bottlenecks. It's all about making sure your information flows smoothly through the system. Ultimately, this leads to faster processing times, quicker responses, and better use of those powerful GPU and TPU. Okay, let's talk about how to speed up your training with multiple GPU. When dealing with massive models and huge datasets, simply relying on one GPU just won't cut it. So, what are our options? The first big technique is data parallelism. Think of it like dividing the work among several teams. Each team gets a chunk of the data, trains its own copy of the model, and then they synchronize their results to make sure everyone's on the same page. Next up, we have model parallelism. This involves splitting the actual model itself across multiple GPU. It's useful when your model is too big to fit on a single device. Then, you can combine these approaches with hybrid parallelism for even greater efficiency. The best strategy really depends on how your specific model and data are set up. Okay, so let's talk about gradient checkpointing. When you're training massive AI models, they can really gobble up all your GPU memory, especially during backpropagation. That's when the model learns from its mistakes. Gradient checkpointing is a clever technique to combat this. Essentially, it cleverly decides which intermediate calculations to store and which to skip. It recalculates those skipped calculations during the backward pass, which takes a bit more time but lets you train bigger models with larger batches all while staying within your memory limits. Okay, let's talk about getting the most out of TPU. They're not just a faster GPU, they're fundamentally different. The first thing you need to do is optimize your data layout. TPU have a preferred way of organizing your data, and if it doesn't match what your model expects, you'll lose *10* of speed. Next, look for opportunities to fuse operations together, like combining several small calculations into one big calculation. This minimizes memory access. Quantization, using less precise numbers, can also dramatically speed things up, but be mindful of potential accuracy trade-offs. Don't forget about XLA compilation. It's the compiler that really unlocks the TPU potential. And finally, pay close attention to padding strategies because these can have a big impact. The best way to know where to focus your efforts is by profiling your model on the TPU itself. Use those tools to find the biggest bottlenecks and prioritize your optimization. Okay, let's talk about XLA and how it's making TPU truly shine. Think of TPU as specialized supercomputers built specifically for the math needed in deep learning, especially matrix multiplications. But just having a powerful processor isn't enough. You need to tell it how to do things efficiently. That's where XLA comes in. XLA is basically a smart compiler that takes your machine learning model, figures out how to best execute it on a TPU, and then generates optimized code for the TPU. It does this by aggressively optimizing the entire computation graph, finding ways to combine operations and reduce wasted steps. Essentially, it's like having a master optimizer that understands exactly what TPU can do best. Okay, let's talk about getting the most out of your GPU when you're training with TensorFlow. First off, think about data types. Using float16 or bfloat16 can drastically reduce memory usage and speed things up significantly. Then, it's important to find the right batch size. Larger batches are generally better for throughput, but make sure your GPU isn't running out of memory. Next, we want to use df function. This compiles your TensorFlow code into a more efficient graph that can take advantage of the GPU. Don't forget about XLA compilation either, it's like an extra layer of optimization. And finally, if you're struggling with memory constraints, gradient accumulation is a really useful technique to simulate larger batches. Okay, let's talk about how GPU manage their memory. Think of GPU memory as a limited space. You want to use it as efficiently as possible. When we're programming for the GPU, we have two main ways to allocate memory: static and dynamic allocation. Static memory allocation is like reserving a block of space upfront at compile time. It's simple and fast because you know exactly how much space you need. However, if your data size changes or you don't use all that reserved space, it's wasted. Dynamic memory allocation, on the other hand, is like asking for memory only when you need it during runtime. It's more flexible, great for handling variable-sized data, like images of different resolutions. But because you're constantly requesting and releasing memory, there's a bit of overhead involved. So, the key is to carefully consider your application's needs and pick the strategy that gives you the best balance between flexibility and performance. Let's talk about how we can make convolutional layers run much faster on GPU. CNNs, especially with deep architectures, require ton of computation, and that's where GPU really shine. They're designed for parallel processing. Think of them as having many tiny brains working together. One key strategy is warp scheduling, which basically means arranging data in a way that makes the GPU groups of instructions, called warps, work more efficiently. Also, utilizing the GPU-owned memory, shared memory, is crucial for speed. Then there are techniques like loop unrolling and vectorization that help transform our code to take full advantage of the GPU capabilities. For convolution operations specifically, things like tiled convolution and algorithms like Winograd's reduce the massive number of multiplication and addition steps by breaking them down into smaller, more manageable pieces. Okay, let's talk about how we get models to run faster on GPU and TPU. We have two main approaches: data parallelism and model parallelism. Data parallelism is like having multiple teams working on the same project. Each team gets a copy of the whole thing and works independently on different pieces of data. They then share their results, but it can be slow because they need to constantly communicate with each other. Model parallelism, on the other hand, is more like dividing the building into sections. Each section or accelerator handles only a part of the model's computations. This is really important when you're dealing with huge models that won't fit onto one device. However, because these accelerators are working separately, they need to talk to each other frequently, which can also create bottlenecks. The best strategy depends on how big your model is and what kind of hardware you're using. Okay, let's dive into profiling and debugging GPU applications. Profiling is essentially your detective work. It helps you figure out where your application is spending most of its time, specifically where performance bottlenecks are hiding. We have a few great tools to use like NVIDIA Insight Systems, AMD Radeon Pro Render Profiler, and Intel V-Tune Amplifier, each offering different levels of insight. Then, debugging goes beyond just spotting problems. It's about actually finding why they're happening. This can involve stepping through GPU code with specialized debuggers, tackling issues within your custom kernels, and even using tools to catch memory corruption, things like pointer errors or leaks that can cause crashes or unpredictable behavior. It's all about understanding how your application is truly performing on the GPU. Let's talk about how we can really see if a TPU is giving us a performance boost. First, you need to pick a deep learning task that's representative of what you actually do, maybe image classification or object detection. Then, get your data ready and make sure both your GPU and the TPU are set up identically. It's important to establish a baseline with your GPU first so we know how much better, or worse, the TPU is performing. We'll log everything: training time, inference time if you're using it, memory usage, and how quickly things go through. Finally, let's compare the numbers to see exactly what the TPU brings to the table. Okay, let's talk about how we structure our code for optimal performance on GPU and TPU. It all starts with threads and blocks. They're the building blocks of parallel computation. Think of it like this: you want to make sure your hardware is working as efficiently as possible, and that means organizing your calculations in a smart way. We need to consider things like occupancy, which is how many threads are actually doing work at any given time compared to what's available. Warp size, the number of threads grouped together, can also significantly impact performance. Larger blocks generally reduce startup costs, but might not always be ideal for all types of problems. So, we often use large blocks for data parallel tasks where lots of similar calculations need to be done on different pieces of data, and smaller blocks when things are more independent. And remember, experimentation is key. Profiling your code with different configurations will help you find the perfect balance. Okay, let's talk about warp divergence. It's a sneaky performance killer when you're programming for GPU. Basically, a GPU works by executing groups of instructions called warps, but if different threads within that warp take completely different paths because of things like if statements or data dependencies, the GPU has to waste cycles figuring out which path each thread needs to follow. It's like having a whole team doing entirely different tasks simultaneously and efficient. To avoid this, you can use techniques like predication, where you tell the GPU before and which threads are going to take each branch. Reordering your data and loop unrolling can also help by making sure threads within a warp work on related information, minimizing those branching issues. Okay, let's talk about a really important concept in Q to programming: occupancy. Think of your GPU processing units like busy workers. Occupancy is simply how many of those workers are actually doing something at any given time. High occupancy means you're making the most of your GPU potential, but too high can cause bottlenecks because everyone's fighting for resources. We want to find that sweet spot where we have enough activity to keep things humming without creating delays. We can adjust this by using multiple streams to overlap different parts of our computations and also experiment with block sizes. Finding the right size is key. And finally, if your threads are all taking wildly different paths through their code, it's like a chaotic construction site, so we want to minimize that thread divergence to keep things running smoothly. Let's talk about a clever trick to speed up GPU and TPU computations: shared memory. The main problem we face is that global memory, the RAM your computer uses, can be slow. It's like everyone trying to use the same hallway at once. Shared memory is in the chip itself, much closer to the processing units. By copying data blocks onto this fast local storage, we drastically reduce the time it takes to access those crucial pieces of information, boosting performance and allowing us to do more in less time. Think of it as having a personal stash of important ingredients for each shift. Okay, let's talk about a clever trick for speeding up GPU and TPU data transfers. It's called pinned memory. Basically, when you allocate memory on a device like your GPU or TPU, you can tell the system to keep that memory spot locked in place. This means it won't get swapped out of RAM like regular data might. The result? The device gets direct access to the CPU memory without having to constantly copy information back and forth, which drastically cuts down on delay and boosts overall speed. Okay, let's talk about speeding up your deep learning models with TensorRT. TensorRT is like a super efficient engine for your GPU. It takes the model you've trained and really tunes it to run faster on NVIDIA hardware. It does this by looking at how your model works, basically figuring out which steps can be combined and made more efficient. Think of it as streamlining the whole process. It automatically optimizes things like merging layers together, choosing the best algorithms for each part, and even reducing the precision of the numbers used in the calculations if you want to shrink the size of your model and speed things up even further. You convert your original model into a TensorRT engine file, let it optimize itself, and then you're ready to deploy it on your GPU. Okay, let's talk about getting your ONCs models running smoothly on GPU. The key here is optimization. Think of it like fine-tuning a race car engine for maximum speed and efficiency. We'll cover some important techniques. First, quantization is really helpful. It reduces the size of your model and the amount of data moving back and forth between the CPU and GPU, which can make a huge difference. Then there's operator fusion, basically combining multiple operations into one, making things faster. Next up is layout optimization, aligning your tensors to take full advantage of the GPU architecture, particularly tensor cores. And finally, consider pruning or weight sharing if you want to really slim down the model without sacrificing too much accuracy. The ONCs optimizer can automate a lot of these steps for you using Python code. It's a great tool. Just load your model, run the optimizer, and save the optimized version. Don't forget to test it out on your GPU and measure the performance improvements. Okay, let's talk about how to make sure your multiple GPU are actually working together efficiently. When you have more than one GPU in a system, it's not enough just to throw all the work at them. We need to distribute it smartly. There are two main approaches. We can assign tasks directly based on what each GPU is good at, that's static load balancing. Or we can dynamically adjust things during runtime, which is called dynamic load balancing. A really popular technique here is work stealing. Think of it like this. If one GPU has a lot of work and another is sitting idle, the busy GPU will take tasks from the idle GPU until both are balanced out. It's a smart way to ensure everyone's contributing and no single GPU gets overloaded. Choosing the right technique depends on your specific application and how you've set up your GPU. It's all about getting the most performance possible. Okay, let's talk about getting your deep learning models to train faster by using multiple GPU or TPU. Horovod is a fantastic framework that makes this easier than you might think. Basically, it's all about distributing the work. Each GPU tackles a piece of the data, and then they all come together to share their calculations and updates. It's like a team project where everyone does their part and then reports back to the leader, though Horovod doesn't actually need a central leader. It leverages MPI for efficient communication between those GPU or TPU, which is really key to scaling up your training process. And best of all, it handles a lot of the complicated details behind the scenes so you can focus on building your model. Okay, let's talk about tackling those massive models. When we train huge AI systems like the really big language models, they can easily run into memory problems on a single GPU. Pipeline parallelism is a clever way to solve this. Basically, it breaks down the model into smaller parts layers, if you will, and assigns each of those parts to a different GPU. It's kind of like an assembly line, where one GPU does its bit, passes the result along, and then the next GPU takes over. This allows us to process data in parallel, dramatically speeding up training time. However, there are some trade-offs. It can increase the overall latency because each stage has to wait for the previous one to finish. Balancing the workload across the GPU is also important to make sure everything runs smoothly. Okay, let's talk about Zero Redundancy Optimizer. It's a really clever way to tackle the huge memory demands when training gigantic AI models like those powering large language models. Basically, Zero tackles this problem by cleverly splitting up all the information involved in the model training process, things like the model's parameters, optimizer states, and even gradients across multiple devices, primarily GPU or TPU. It's not just about spreading things around, it's strategically doing so to remove redundancy. Think of it like this: if you don't need a particular piece of information at a specific moment, Zero moves it off the primary GPU memory and stores it elsewhere, potentially on CPU, RAM, or even NVMe storage. There are actually 3 levels of Zero. Zero-1 focuses on moving parameters, Zero-2 tackles optimizer states, and the RO-3 goes further by implementing full batch sparsity. All these techniques combined allow us to train models that would be impossible to fit in a single GPU memory, opening up the possibilities for much more complex and powerful AI. Okay, let's talk about how we can really squeeze extra performance out of our deep learning models. We've already seen how GPU and TPU are amazing accelerators, but they need to be working efficiently. That's where graph optimization comes in. Think of a computational graph as a blueprint for your model. It shows every operation that needs to happen. The frameworks like TensorFlow and PyTorch do some basic optimization automatically, but you can go deeper. We're talking about techniques like constant folding, which basically replaces things like 2 plus 2 with just 4. Then there's operator fusion, combining multiple steps into one big step that the hardware understands better. Layout transformations are all about how data is arranged in memory to make it easier for the GPU or TPU to access it. And finally, dead code elimination just gets rid of anything that isn't actually used. Frameworks give you tools like XLA and TorchScript to help you manage these passes. It's a powerful way to get the most out of your hardware. Okay, let's talk about auto-mix precision scaling, a really cool technique for boosting performance in PyTorch and TensorFlow. Basically, it's all about using low-precision floating point numbers like F16 half-precision alongside standard FP32 without sacrificing accuracy. Think of it as giving your hardware a little boost. PyTorch uses the TorchCUDA AMP library to do this automatically, managing the scaling and adjustments behind the scenes. TensorFlow employs techniques like TF-train. Optimize the wrapper or the more modern mixed precision strategy for similar results. By intelligently switching between F16 and FP32, we can drastically reduce memory usage, speed up calculations on GPU and TPU, and ultimately train models faster. Let's talk about how we can make our deep learning models run faster and take up less space. A really helpful technique is called quantization. Basically, it's like shrinking the numbers representing our model's values. Think of it as rounding them off to a lower precision level. We have two main options here, F16 and int8. F16 uses half the bits that FP32 does, which means a smaller model size and less memory needed. But because it's less precise, you might see some instability during training, especially with very deep networks. On the other hand, int8 uses just 8 bits per value, even more compact. This is fantastic for speed, particularly on hardware that's specifically designed to handle int8 operations like TPU. The downside? You could lose a bit of accuracy if you're not careful. It's really about finding the right balance between size, speed, and maintaining good performance, and calibration techniques are key to helping us achieve that. Okay, let's talk about gradient accumulation. Sometimes, you want to use a really big batch size during training that can speed things up considerably. But your GPU might not have enough memory to handle it directly. That's where gradient accumulation comes in. It's like tricking the system into thinking you're working with a much larger batch than you actually are. You process data in smaller chunks, calculate gradients for each chunk, and then accumulate those gradients instead of applying them right away. You do this several times over, and finally, when you've collected enough accumulated gradients, you apply them to update your model's weights. It's a clever way to get the benefits of a huge batch size without running into memory issues. Okay, let's talk about scaling deep learning training, specifically how we can handle really large data sets and models. We're moving beyond a single GPU or TPU and into the world of elastic distributed training on clusters with diverse hardware. These clusters might have different kinds of accelerators, like GPU and TPU, each with their strengths and weaknesses. The goal is to be able to quickly add more resources when needed. That's elasticity. We use techniques like data parallelism and model parallelism to split the workload, and it's really important to minimize communication between these devices because that can slow things down. Kubernetes helps us manage everything, and frameworks like TensorFlow with features like XLA are designed for this kind of hybrid environment. Finally, we're able to dynamically adjust how many workers and what type of accelerators we use based on the training progress, really optimizing resource utilization. Okay, let's talk about kernel launch overhead. It's a really important concept when we're looking at how GPU and TPU accelerate our code. Basically, it's the time it takes to get things ready before your actual computation starts. It's like starting up a complex machine. There's always some setup involved. This includes tasks such as figuring out which core will run the kernel, switching between different kernels, allocating registers for data and storing results, and setting up the memory space the kernel needs. It can be a significant bottleneck if you're launching many small kernels or calling them frequently, so minimizing this overhead is key to getting the most out of your hardware. Okay, let's talk about getting your CPU and GPU working together smoothly. It's really important to avoid bottlenecks when transferring data between them, and that's where synchronization comes in. There are a few common problems you can run into, things like race conditions where multiple threads try to access the same information at once, or data dependencies where one part of your code needs something from the GPU before it can continue. And sometimes just the act of moving small chunks of data back and forth repeatedly can cause delays. Luckily, there are some great solutions. NVIDIA's Q2 streams let you overlap computation and communication, which really speeds things up. Hybrid models using OpenMP for CPU tasks alongside CUDA on the GPU is another good approach. And pinning memory, making sure specific areas of the GPU are easily accessible by both sides, can help reduce those data transfer lags. Finally, asynchronous transfers allow you to start sending data from your CPU without waiting for it to be ready, letting things happen more quickly. It's all about picking the right strategy for your project. Okay, let's talk about getting GPU running smoothly in Kubernetes. Kubernetes is fantastic at managing containers, but directly giving pod access to a GPU can be tricky. The key is careful planning around node affinity. We want to make sure that pods needing those powerful GPU are actually scheduled on nodes that have them. We used hints and labels to help identify which nodes have GPU and what kinds of workloads they're suited for. Then device plugins like the NVIDIA device plugin take over, dynamically managing the connection between the pod and the GPU, essentially handling all the communication behind the scenes. Think of it as a smart intermediary that makes sure everything works together seamlessly. Okay, let's talk about getting the most out of your GPU when running inference servers. The first thing you need to do is find out exactly where your bottleneck is, whether it's a specific layer in your model or something happening during data transfer. Then try increasing batch sizes. Bigger batches can really help leverage all those parallel processing capabilities in the GPU. Don't forget about mixed precision training. Using F16 can significantly speed things up without sacrificing too much accuracy. You might also explore techniques like layer fusion to combine operations into a single step, and for custom kernels, optimizing how data is accessed can make a big difference. And finally, always keep an eye on your processing pipeline. If that's slow, it'll hold back the entire inference process. Okay, let's talk about how we tackle those huge embeddings that come with modern language models. These embeddings, think of them as numerical fingerprints for words, can get incredibly large, quickly pushing the limits of what a single GPU or TPU can handle. The main problems are memory constraints and the sheer amount of computation involved. Fortunately, there are several clever techniques we use. We can reduce the precision of these embeddings using quantization, which shrinks the size quite a bit. Another approach is embedding lookups. Instead of storing every individual embedding, we create smaller tables to retrieve them. Also, sometimes we need to offload parts of the embedding layer to CPU memory. Techniques like gradient accumulation and mixed precision training also help us manage things effectively during training. Okay, let's talk about weight pruning, a really clever way to speed up your deep learning models. Imagine you have a huge neural network, and it's taking up a ton of memory and time to run. Weight pruning is like giving it a haircut. It identifies the less important connections in the network, basically the weights that aren't contributing much to the final prediction, and removes them. It's all about strategically making the model smaller without sacrificing too much accuracy. You score the weights based on how important they are, set a threshold, and then fine-tune the pruned model to make sure it still performs well. It leads to smaller models, faster processing, and less energy use, perfect for devices with limited resources. Okay, let's talk about memory tiling, a clever trick for speeding up GPU calculations. The problem is that when we're dealing with big matrices, they often don't all fit comfortably in the GPU fast memory cache. This means the GPU has to constantly go back and forth to slower main memory, which really slows things down. Memory tiling solves this by breaking those huge matrices into smaller, manageable chunks. We call them tiles or blocks. Instead of processing everything at once, we operate on these tiles locally within the cache. It's like doing a small job then putting the pieces together. This minimizes how often the GPU needs to grab data from main memory and significantly boosts performance. It's all about keeping that precious cache full. Okay, let's talk about how we balance speed and efficiency when using GPU for AI. When you're running an inference that's basically getting a prediction from your model, there are two things you really want to optimize: latency and throughput. Latency is simply how long it takes to get one answer back. Think of it like the time it takes for your app to respond after you click a button. We want this to be as short as possible, right? And throughput is all about speed. How many questions can your system answer in a given amount of time? Now here's the catch: if you try to make things super fast by processing more data at once, increasing batch size, it often increases latency because there's more data to move around and process. Simultaneously, increasing throughput means you might need a more complex model or more powerful hardware, which can also slow things down. It's all about finding the sweet spot where your application gets the speed it needs without sacrificing too much responsiveness. Okay, let's talk about deploying your models on Google Cloud TPU. They're fantastic for handling massive datasets and complex computations. Think huge training runs. The first thing to remember is data. You need to split your data efficiently across the TPU core so they can work together smoothly. TensorFlow data services can really help with this, or you might design a custom sharding approach. Next up is model optimization. TPU are great at working with XLA compilation. That means aggressive optimizations and faster processing. Batching is key too. Experimenting to find the right batch size will significantly impact your training speed. And finally, always have a solid checkpointing strategy in place for those long runs. Okay, so let's talk about taking your deep learning training beyond a single TPU or GPU. When you're dealing with really large models and datasets, scaling up to multiple pods can be a game changer, reducing training time significantly. But it's not just adding more hardware. There are some important things to consider. First off, we need to think about how these pods are connected. The topology matters. Then, you'll want to figure out how to divide your data across those pods efficiently. Different partitioning strategies like data parallelism or tensor parallelism have their own advantages and disadvantages. Don't forget that communication between pods introduces latency, so optimizing how data is moved around is key. And lastly, make sure your training software like TensorFlow or PyTorch is set up to work well in a multi-pod environment. It's really important to experiment with smaller configurations first to find what works best for your specific model and data. Okay, so today we're talking about how to really understand what's going on when you run your TensorFlow models on TPU. We'll focus on using TensorBoard and the TPU tools for profiling, basically figuring out where the bottlenecks are in your workflow. TensorBoard lets us visualize execution timelines, pinpointing things like a CPU, GPU or the TPU itself is holding up the process, and understand how much memory is being used. Then we have the TPU tools, which provide very specific insights into the TPU behavior, things like the number of times kernels are launched, the size of activation, data moving around, and even overhead related to transferring information between components. You'll run your TensorFlow program on a TPU, then use TensorBoard to launch an interface that lets you see all this data visually. And when looking at the TPU tools, we want to focus on things like excessive data transfers or inefficient kernel launch, as these are usually the first places we can make improvements. Okay, let's talk about making TPU work faster for really big TensorFlow models. When you're dealing with massive graphs, think huge datasets or complex neural networks, the initial compilation process can be major bottleneck. It takes a while for the TPU to understand and optimize your code. So how do we speed things up? First off, we want to simplify our graph as much as possible, removing anything that's not being used and combining operations where it makes sense. Then, model parallelism can help. Splitting up the model across multiple TPU cores reduces the workload on each individual core during compilation. Experimenting with different compilation flags is also key. Higher optimization levels ** lead to faster execution later on, but they increase the initial compile time. Finally, for modular graphs, precompiling smaller sections separately can dramatically improve speed. Okay, so let's talk about custom ops, basically adding your own specialized functions to the GPU toolbox. Often, the pre-built libraries don't have the most efficient way to handle certain calculations or models. By creating a custom op in C++, you can write your own kernels that are perfectly tailored for the GPU, giving you a major speed boost. It's like having a supercharged version of an operation just for your specific needs. The process involves defining the kernel, compiling it, and then registering it with frameworks like TensorFlow or PyTorch so they know to use it. Okay, let's talk about how GPU and TPU handle situations where the output size of a model changes depending on what we feed it. Think about models like transformers. They can produce vastly different outputs based on the input text. This means that traditional acceleration methods, which often rely on fixed batch sizes and pre-allocated memory, struggle with this dynamic nature. GPU models are tackling this head-on using clever tricks. They use techniques like dynamically routing experts, a mixture of experts layers, focusing only on the parts of a tensor that actually need processing. We call that sparse operations, and smartly allocating memory is needed during inference, so no resources are wasted. Essentially, they are making dynamic shapes work efficiently on modern hardware. Thank you for watching.